I'm going to talk to you today about, or briefly today, about three projects quickly. Titled is Three Generations of High Performance Design, because I want to show you what green thinking was in terms of architecture and sustainability, just in terms of energy, from a building that was designed in 1996, 4 Times Square, not one of our projects, but a very green building designed by Fox and Fowle. Another project, One Bryant Park, which Susan mentioned. I'll go into that into a lot more detail because we designed that and it's now completed, or very close to complete, and we have a lot of data about it. And then the next generation building, which is a building we are working on currently called 1 Congress Street in Boston, which has just started the design process, and we can talk a little bit about what we're trying and how we're going to go to the next step forward from One Bryant Park. The first project is 4 Times Square. This is 4 Times Square here. It's a 1.6 million square foot office building, started design in 96, completed in around 2000. It's occupied by Condé Nast and Skadden Arps, a law firm and a magazine publisher. This was really considered the first green office building in the United States. The idea from the developer's point of view was to set the bar and to try to get other people to copy them. One of the things they were disappointed in is that not a lot of people were copying them. Not a lot of people stepped up at the time when they were designing this and when they first got it out there in the public. And they were really hoping that One Bryant Park would really set that bar next and encourage the current marketplace to move in that direction. And hopefully we've succeeded in that. It's gotten enough publicity, we think, that hopefully a lot of people have learned from what we've done. So some of the steps that they tried at 4 Times Square, which were not as successful as they had hoped, but were very interesting for the time, is they included fuel cells in the building, which provided about 10% of the power demand of the energy demand for the building. Photovoltaics, which there's a couple photovoltaic arrays up here and up here, as well as a couple other minor measures. What was interesting is what they learned here was that the fuel cells really weren't the most effective way of producing power for the building. They were very high maintenance, very difficult to maintain and keep running, hard to get into the building. They actually occupied a tremendous amount of space for a relatively small amount of energy that was being produced. So they realized that fuel cells, at least for this type of building, was not the most effective and best use of the money that they're spending and for the bang for the buck, basically. The photovoltaics, which are, like I said, up there, same story. Unfortunately, not for this type of building, not the right way to install or use photovoltaics. Unfortunately, they're on the vertical face on these walls, and really photovoltaics should be angled. They really should be at an angle at about whatever your latitude is. That's the angle from horizontal that you really should have your photovoltaics at for their peak performance. Really, they should track the sun. But if you're going to have them on a set angle, then that's the right number. Doing it on a flat surface means they're producing very little power, really, and very expensive, again, to maintain and keep running. So they were trying something here. They were making some experimental steps forward, trying to do the right thing and seeing what they could get out of it. Didn't quite get what they wanted, though. So, same developer, working on the site next door. This is 4 Times Square. This is our building here, called One Bryant Park, also called the Bank of America Tower. This is a new 2.2 million square foot office building, so bigger, slightly bigger than 4 Times Square by about, 600,000 square feet. Obviously considerably taller than 4 Times Square, and has another very high energy demand tenant, the Bank of America. This is essentially a trading operation. Trading operations are probably the most highest energy demand tenant that you're going to get in a building like this, other than straight data centers. The building's almost complete. As you can tell, we're just pulling off the hoist here and just finishing up this side of the building. It's fully occupied up to about this level at this point, even though we're still constructing the building. It's amazing what you can do when you're building a building these days. Actually, it's been occupied for almost a year at this point. But in terms of energy, and I'm just going to talk in terms of energy on this building, there's a whole lot of other steps, but just in terms of energy, what we wanted to do first when we started looking at this building is seeing what we could do for free. What is available to any architecture, any building, what's available to us for free. We're not necessarily going to use these technologies, but we need to study them and see what's available to us. The sun, we did study to see if photovoltaics had advanced since 4 Times Square, or if we could find some way to incorporate them into a building. In New York City, on a tall vertical building, it's just not really feasible to do. And the power that you're generating just doesn't make a lot of sense on a building like this. A big open plan building, like a manufacturing plant, something with a big huge flat roof, makes a lot of sense. Not here. Rain is a resource. We collected all the water, but we're not going to talk about that. Biology, earth, and wind are all potential sources of energy, and I believe we're going to hear a lot more about wind later. On One Bryant Park, none of these really worked out for us. The anaerobic digesters, we studied it to see if we could put them into the building. It was an idea, but it hasn't really gotten all the way yet. Geothermal wells, using the earth as a source for heating and cooling, is potentially still there. Is a potential source of heating and cooling for a very small portion of the building. And wind, we don't really have a consistent enough wind source in New York City to really promote wind on a large scale on buildings of this type. These are all the first things you look at. But the real story on One Bryant Park is cogeneration, is a method of generating significant amount of power on site in a very clean and effective and efficient way. Real quickly, one of the problems is the way we generate power. These are power transmission lines running across pretty much anywhere in the world. You'll see these. This is an art installation. These are fluorescent tubes that are just stuck into the ground with no wires that are connecting them. And the stray power, the stray current that's coming off those power lines is really lighting up these electric wires, or the fluorescent tubes. That's not real. You're not really it's not really the electric power that's lighting these. It's the current that's generated around the lines. But it does sort of express the idea that we lose a lot of power over transmission lines. So the problem in New York City and almost any city is the way that we generate power. We generate power off-site in a traditional coal plant or whatever power plant, or whatever fuel source you're using. About 66% of the energy goes straight up the smokestack, is unusable, it's just lost as heat. Another 7% gets lost over the transmission lines, and by the time it gets to your building, you're only getting about 27% of the energy that's coming out of that fuel source. A really inefficient way of producing power. What we're doing at Bryant Park is we are building our own cogeneration plant, our own power generating plant. It'll generate 4.6 megawatts of power, which, to give you an idea of what that is, it's about 5,000 homes, and it's generated in an extremely clean way, where we lose very little up the smokestack. There is some loss, about 23%, but we get 77% usable energy, so 3 times more than what you get out of the traditional power distribution system. A much better, efficient, cleaner way of producing power for the building. And it's the first building that's really included this in a large scale in a single building. You'll see them on hospitals and in university complexes, but never in a large scale building of this type. The other step we did was incorporate a ice storage system, or thermal storage system, into the basement of the building. There's 44 of these tanks. They get frozen solid during the day, during the night, and then during the day we use that ice to help cool down the building. This is actually a very ancient technology. The Romans used a system very similar to this. This is just the high-tech version of it. What this does, I'll go back now. The real problem in a lot of the energy grid is this curve right here. This is a demand curve for most buildings. In the middle of the day, you have a cooling demand and a base load demand. The base load demands your computers and the building systems that are running, and then your air conditioning demand. This peak demand is peaked in every building across the city all at the same time, and that becomes a problem for the whole city, because when we have, in the middle of the summer, we have peaker plants which generate all that excess power you need just at that one particular time of day. Those peaker plants are our dirtiest plants, our nastiest plants. They produce these fantastic sunsets, because pollution equals sunsets, but we're also polluting our atmosphere dramatically. What Bryant Park does is, instead of having this type of curve, our curve is much more like this. It's not exactly that, but it's close to this. It's much flatter and much lower than this peak demand at that particular point, which is, by taking our ice, making it during the night, you take this cooling load and shift it into the nighttime. Just an efficient, smarter way of producing power. Also cheaper, because we get charged off of our peak demand loads. This shows where our cogeneration is, how it feeds into a generator, basically showing how all the systems are interconnected. These all have to be designed in tandem and thought of all at the same time. Again, there's too much detail in here to really talk about too much. But you can tell all these systems are interrelated, so you have to really be thinking about the building all as one giant system at the same time, not as discrete pieces of each of the building. It goes right onto the floor, and how the air is distributed onto the floor, where the cooling is coming from, how that heating is coming, how the excess heat comes out of the building. It's all thought about all at the same time. And the last step here is commissioning. In any major building, it doesn't really matter what you're designing, it has to be running effectively. That means there's a last step called commissioning, where a third-party observer comes into the building and investigates the whole building to make sure that it's operating up to the specifications that we've all designed. The next step after this is in the operations of the building. Not only is it important how we design it, how we make sure it's running properly, but in the long-term lifespan of the building, it's continually operated properly and up to the specifications that we all established. Fortunately, in this building, the building operators were with us through the entire design process, which almost never happens. And that in the first design meeting, the building engineer of the building actually sat in the design meeting and engaged with us in how we're going to operate this building and function it. So that he actually knows why we did what we did and the reason or where everything is and how the building actually is supposed to function. And he contributed to that at the same time. All right, so that was what we did today, which is a good leap forward in terms of and what you can do in terms of design from today's point of view. And now we're going to talk about the next project that we're working on, which is called 1 Congress Street in Boston. This is our site right here, this giant 2,400 car garage. The site actually extends to here as well. And we're building a new 3.5 million square foot complex with 2 office buildings, 2 residential buildings, 2 hotels, all combined into one large complex. The goal here is to take Bryant Park as the base point and then step forward from that to see if we can make a large complex both LEED Platinum, if not more than that. So this is our design, which we recently won a competition for about 2 months ago. This is the first office tower, the second office tower, 1 hotel, second hotel, a residential building here, and then they're debating whether to put a residential component into the base of this building. This is a very large project for Boston, this is probably the biggest development Boston's had in the last 30 years or so. As you can tell, there actually isn't a heck of a lot of new development in Boston. It's a very difficult city to build in. It just hasn't developed a lot recently. And this will be by far the greenest building in the city. There's a lot of motivation in the city from the mayor and from some of the other governmental organizations to push green development forward. This is just a blow up of the base where it's trying to fit into the neighborhood fabric. This is a very early design study. It's about 2 weeks into the design, so the actual shape and form of the building is still very much in flux. But what we're trying to do here is take the next step forward in terms of energy. What we looked at is that Boston has a goal of trying to meet 80% CO2 reduction by 2050. It's a very steep goal. It's very hard to meet, but we're going to see what we can do in this building to try to make sure to try to contribute to that. What we did here is look at how we could possibly achieve that. The first step is to reduce consumption. That's showing a 10% reduction in CO2 by reducing consumption. This is the hardest single step that we're going to have to do, and really we have to do this on buildings as a whole. Buildings are designed to have a very high energy demand side. So basically our leases are written so that we have to supply a large amount of power to all of our tenants. Our goal here is to reduce their power needs in the first place. It's very hard for us to do. It's a kind of political problem with us and the brokers and the building owners to try to achieve that. 10% is a healthy goal. We think we can do 20 or 30% and not reduce any performance, but that's going to take a lot more convincing. We are going to look at photovoltaics and wind turbines. Wind actually works in Boston. There's a much more consistent wind than there is in New York. We also have more exposure here than we would have in One Bryant Park. We also have a much larger site with a much larger roof area, so we're thinking we could also incorporate photovoltaics. That's still a very small percentage of the actual power or CO2 load on the building, but we think there's some opportunity here. The biggest side, again, is cogeneration. In this case, we've got a larger complex, and we've got a slightly different way that the city distributes power and steam in the city overall. So we think we can incorporate not a 5 megawatt cogen plant, or 4.6, but a 15 megawatt cogen plant. This is about 175% of the building's power demands over a full year cycle. And the idea here is that we would be able to provide power into the city grid, and as well as produce steam that could also go into the city grid, so we could sell the excess power that we're producing on site in a clean and efficient way. This is also government center. This is where all the major government buildings are in the city, and this would be one way of reinforcing the current infrastructure in the city. If you're curious, that's what a cogeneration turbine looks like. It's really a jet engine. It's a natural gas jet engine, same thing they put on a 747, and you somehow have to incorporate it into your building. Not the easiest thing to do in the world. There's a lot of tricks in trying to put in one of these systems in, but it really is the next, we think at least, the next generation of what we can do in terms of design and energy on buildings. Still a little image of just how we're designing the floor slabs. It's a much more efficient floor slab construction system than you'd see in One Bryant Park. It's taking what we learned there and going the next step forward. There's a couple details in here that probably too detailed to get into in this conversation, but just knowing that we can do things differently on a floor-by-floor basis and still improve the performance even at what is today's state-of-the-art is not tomorrow's state-of-the-art. There's a lot of opportunities for us to move forward in the next few years as long as we have people who are dedicated like you all, professionals like myself, and owners who are really interested in making the next step forward. So thank you very much.